In this video, I would like to elaborate all of my answers of the final exams computer architecture. My name is Ihsanul Arifin Ramadhani and my NIM is 41522010249. For the number one is to estimate the maximum aggregate I/O transfer rate in the given system. We need to consider the transfer rates for each device and the number of devices connected to the selector channels and the multiple XOR channel. For the selector channels, each selector channel supports two magnetic disk units and two magnetic tap units. For magnetic disk is 100 kilobytes multiplied by 2, so 1600 kilobytes, and total transfer rate for magnetic tapes is 200 kilobytes, so also multiplied by 2, so 400 kilobytes. For the multiple XOR channel, the multiple XOR channel has two line printers, two card readers, and 10 VDT terminals connected to it. Total transfer rate for line printers 6.6 kilobytes multiplied by 2, so 13.2 kilobytes, and total transfer rate for card readers is 1.2 kilobytes, so which means 2.4 kilobytes. Total transfer rate for VDT terminals is 10 kilobytes per second. So the aggregate I/O transfer rate, aggregate transfer rate, which means transfer rate of selector channels plus transfer rate of multiple XOR channels. For the total transfer rate is, as I mentioned before, 1600 kilobytes per second for this, and 400 kilobytes for tapes, 13.2 kilobytes for printers, and 2.4 kilobytes for readers, and 10 kilobytes for terminals. So calculating the total aggregate transfer rate, 1600 plus 400 plus 3.2 plus 2.4 plus 10 kilobytes per second. So the total aggregate transfer rate is 25.6 kilobytes per second. Therefore, the maximum aggregate I/O transfer rate in the system is approximately 2025.6 kilobytes per second. For the number 2, consider a page logical address space composed of 32 pages and of 2 kilobytes each, mapped into 1 megabyte physical memory space. For the A, what is the format of processor's logical address? And for the B, what is the length and the width of the page table, disregarding the access write bits? For the C, what is the effect on the page table if the physical memory space is reduced by half? For the A, the format of the processor logical address would typically consist of two parts, the page number and the offset within the page. In this case, since we have a page logical address space composed of 32 pages of 2 kilobytes each, we would need 5 bits to represent the page, 11 bits to represent the offset within the page. Therefore, the format of processor's logical address would be 5 bits and offset is 11 bits. For the B, the length of the page table would be equal to the number of pages in the logical address space. In this case, we can have 32 pages since each entry in the page table corresponds to a single page, and the length of the page table would be 32 entries. The width of the page table entry would depend on the size of the physical memory space. In this case, the physical memory space is 1 megabyte. We would need around 20 bits to represent the physical memory addresses. For the length, would be 32 entries. For the width, 20 bits. For the C, if the physical memory space is reduced by half to 12 kilobytes, and the width of the page table entries would change, we would now need 19 bits to represent the physical memory addresses. Therefore, the effect on the page table if the physical memory space is reduced by half would be width of the page table entries, 19 bits reduced from 20 bits. For number 3, in many cases, common machine instructions that are not listed as part of MIPS instruction set can be synthesized with a single MIPS instruction. Show this for the following. For the A, register to register move can be performed using the add instruction with a register and 0 as operands. This instruction effectively copies the value from one register to another. For the B, increment decrement, to perform an increment or decrement operation in MIPS, we can use the add-I instruction with a register and immediate value of 1 or -1 respectively. For the C, complement. Perform a complement operation or bitwise negation. MIPS, we can use the NOR instruction with the same register for both sorts, operands, and a register with all bits set to 0 as the destination register. This instruction performs a logical NOR operation between the two sort registers and stores the result in the destination register. For the D, negate. To perform negation, arithmetic negation in MIPS, we can use sub instruction with a register, another register containing 0, and the register to be negated as operands. This instruction subtracts the value in the third register from 0 and stores the result in the first register. For the E, clear. To clear a register or set its value to 0 in the MIPS, we can use the add instruction as well with a register, the 0 register and other register as operands. This instruction adds the values in the second and third register and stores the result in the first register, effectively clearing it. For the question number 4, consider an SMP with both L1 and L2 caches using the MECI protocol. As explained in section 17.3, one of 4 states is associated with each line in the L2 cache. Are all 4 states also needed for each line in the L1 cache? If so, why? If not, explain which states or states can be eliminated. MECI protocol, the 4 states associated with each line in the L2 cache are modified, exclusive, shared, and invalid. However, in the case of L1 cache, not all 4 states are necessary. The L1 cache is typically private to each core or processor in an SMP or symmetric multiprocessor system, small and fast, providing quick access to frequently used data. Due to its design and proximity to the core, it is not directly shared among multiple cores. In this context, the modified and exclusive states are not needed in the L1 cache. These states are more relevant in the shared cache hierarchy, the L2 cache in an SMP system where multiple cores can access and modify the same cache lines. The necessary states for each line in the L1 cache are typically modified, shared, and invalid. So I think let's understand the rules of each state. For the modified or M, this state indicates that the cache line is both modified and exclusive to the current core. It means that the core has modified the data in its private L1 cache and has not yet written in the back to the memory. The core modified cache line in the modified state needs to eventually write the data back to memory and invalidate any other copies in other caches. For the number 2, shared, this state indicates that the cache line is clean and may be present in other cache in the system. It means that multiple cores may have a copy of the data in their respective L1 cache. The data is coherent among these caches, and any core can read that data but cannot modify it directly. For the I, invalid, this state indicates that the cache line is not valid in the L1 cache. It means that the cache line is either empty or has been invalidated due to another core modifying the data, or a cache coherence even. When a core requests data that is in the invalid state, it needs to fetch the data from a higher level cache or memory. By having these 3 states, modified, shared, and invalid, in the L1 cache, the cache coherence protocol can maintain the data coherence within a single core's private cache and ensure proper data visibility and synchronization among cores. In summary, the L1 cache typically requires the modified, shared, and invalid, which is MSI, while the exclusive E state is not necessary since the L1 cache is not directly shared among multiple cores. I would like to say thank you so much, and thank you so much for listening my explanation of final exams computer architecture. Once again, thank you and have a great day.